Bismillahirrahmanirrahim. Assalamualaikum and very good afternoon to all of you. Welcome back to the class. In this video, I will discuss the example 5.4, which is the design of slender column band about the minor axis. Okay, in this video, in this example, you can see that this is the orientations of the plan view, the cross section of the column. The moment at the top given, acting from the action of beams is 25 kN/meter, and at the bottom is 35 kN/meter. Okay, and this is the, let's say this is the cross sections of the column. Okay, this is the, this one. This is the longer side, and it will bend here, bend about the y-axis. So if we refer to this one, okay, this is the rule of thumb. So if it bend about the minor axis, so the h is equal to the shorter side. Okay, if it bend about the minor axis, so now the h is equal to, so this one based on my reading. Okay, this one, let's say this is BH is equal to 250 times 200. Okay, 250 times 200. So here shall be 200 mm. Okay, and it will bend. Okay, it will bend. Okay, this is 250. So this is, let's say the orientation here is, sorry, okay. So 250, 200. Here, and that is for our case now is we rotate there. So let's say this is the h. Okay, sorry, 250. So in this example, it shall be like this one. Okay, this is 200, the side of 200, and this is the 250 mm. Okay, for the previous one in example 5.3, it bend here about the z-axis, and now it will bend here about the y-axis. So the h is the longer or shorter? H is belong to the shorter. So this is the 200 mm. H is equal to 200 mm, and then the B is equal to 250 mm. Okay, H is the shorter side. Okay, so this is balik ya, B times H. So H times B ya. Okay, and then the nominal cover is given as 30 mm, but for this case, you have to check, okay, the creep correction factor you must consider, and then the effective length given here. Okay, slenderness ratio is given as this one. Okay, so you must in order to determine the bending moment, you must consider the first order moment, where the imperfection moment is equal to this one, and ED times the eccentricity, or the eccentricity is equal to L0 over 400 of, let's say the value is the value shall be this one. Actually, the value shall be, you shall check this one. Okay, L0 400, H times 300, or the 20. Okay, this one, this is short, you shall check by this one. Okay, it's okay, please remind me, okay, in our next class about this, where the value of 20. Okay, okay, so you must the value is, okay, 3.3 divided by 400. So this is our NED. NED is here 6 to 5 kilonewton. So the imperfection moment is equal to 5.16 kilonewton meter. So the first order moment, including the effect of imperfections, is this is eccentricity. Okay, the effect of eccentricity means, let's say this is our column. So let's say this is the position of our actual position of NED. So it have some offset here, and then this the offset of 3.3 divided by 400. This is 3.3 divided by 400. The distance, as you know, this is the distance, and then this is the loading, will create moment. This is the imperfection moment. So 25, okay, from the top, and okay, from the top here this is 25, from bottom is 35. Okay, it will give this to value of MO1 and MO2, and then the MOE is equal to, you just use these equations. Okay, you can refer to this book, you can refer to this page. MOE is equal to this one. Okay, so you must refer to this book, and then you can you must, okay, this is the first conditions. It must be greater than 0.4 MO2, but the value is 12.03 and 16.06. So you must if the value here is equal to 20 something, so you use the maximum. Okay, you use the larger one. But here, because the larger one is 16.06, so you use 16.06 as the MOE. Okay, and then the second order moment is NDED times E2, and this is the NED, 6 to 5 km. E2 this is quite complicated, so please be careful. E2 is equal to, you use these equations for E2, but you must determine the C. The C is equal to 10. From this book, you can refer the C, this one. Okay, you can use C equal to 10. Simply use C equal to 10, and this the E2 is equal to the deflections, which is equal to 1 over R, okay, times L naught over C. This is the equation for E2. So this is, okay, 1 over R here. Okay, is the curvature, which is the KR times K phi times 1 over R naught. Okay, and then we can, for the first round, we can assume that the value of KR is equal to 1.0. Okay, based on this one. Okay, because the maximum value of KR, okay, this is the KR. This is KR, sorry. Sorry, class. Okay. The maximum value of KR shall be 1. Okay, because this is, okay, you refer here, the maximum value of KR is 1. Okay, 1 or lesser. Okay, so you, for the first round, you can assume that the value is 1, and then you can check with the actual value of W and N. Okay, so you refer here, the creep factor, okay, is given, and then 1 over R naught is equal to this one. Okay, epsilon YD divided by 0.45 D. Okay, so this one, okay, the curvature, the creep factor is given, and then the 1 over R naught here is FYD. FYD is equal to FYK divided by the partial factor of 1.15, so it's 0.17 times 500, so it's equal to 1 over 1.15 times 10 FYK. Okay, FYK is 500. This is the FYK. Okay, then this is 1 over 1.15. Okay, and then Okay, over ES is elasticity of steel, and then 0.45 times D. Okay, and then this is the value of D. Okay, D is equal to CH minus C nominal minus, okay, this one, D. This, okay, the first one, as I mentioned before, is the value of D2, right? But now we have to check the value of D. So this one, the link. So I hope you are not confused. Okay, this is the value of D2, and this is the value of D. Okay, so D is equal to H 200 minus 30 minus 6 minus 20 over 2 is equal to 145. Okay, 154. Okay, minus, sorry, 200 minus, okay, I'm checking by using my calculator. Okay, so 154 millimeter. So you can use it here. Okay, so this is the D. Okay, please don't confuse between D and D2. Okay, and then the LR is just okay, L over R is here. You use this equation. L over R is the curvature, KR times KV times 1 over R naught. So you can, okay, this is the KR, and then this is the KV, and this is the 1 over R naught. So you can got 1 over R is equal to 3.77 times 10 to the power of -5. So E2 is equal to, so you refer back these equations. Okay, E2 is equal to 1 over R times the L naught over C. So, okay, this is the 1 over, okay, the 1 over R times this is the L naught over C. Why you have square here? This is not L naught square, kan? Okay, no square, no, should be no square. This one, quite confusing, quite confusing. Can you check the calculation? Use your calculator, please. Is it true that the answer is 41.1 mm?
To 4.176.
4.1, 3.77. Okay, this one times the L naught. L naught is equal to 3000 and this one, 3300 millimeters divided by C. C is equal to 10. Boleh cuba buat? 0.0000377 times divide by 10. Saya dapat jawapan ni adalah 0. Apa ni? 0.12441. 41, so it shall be to the power of 2, right? This one is okay, sorry. This one, to the power of 2. So the deflection, L naught. Okay, shall be, this is the right equation. Okay, 1 over R times L naught 2 power 2 divided by C. This is the right equation. You must have this one. Okay. Itu yang example 3.5.3 dia ada itu tak? Tak ada kan? Dia just E not.
Yang itu tu ada square.
Ada square kan?
Ada square, ada square.
Hmm.
Eurocode, dalam Eurocode ada square.
Dalam Eurocode ada square. Okay, thank you.
Ah,
Okay, EI. So this one. Okay, this is okay, so okay, I'm so sorry for this inconvenience. Okay, so ada square. Okay, so this is the right equation. Okay, so you better check. Okay, this one. So the nominal second order moment is equal to N times E2, so 25.7 kilonewton meter. So the minimum is ND times E naught. E naught is H over 30. H over 30, this is right. Okay. So this is the N minimum. So based on these situations, the design moment is you must select between these situations where the MO2, MOE plus M2, MO1 plus 0.5, M2 and N minimum. So you must select. So this is the okay. Let's do it together. Okay, for this example, let's do it together. Okay, I don't want to be confused. So MED is equal to the maximum between the MO2 and MOE plus M2, MO1 plus 0.5 M2 and the M minimum. So the MO2 is equal to, tadi di sini kita dapat MO2 is here, this one, 40.16. So we select the maximum between 40.16 and then MOE plus M2. MOE plus M2 is equal to MOE is 16.06 plus our M2 is equal to, where is our M2? 25.7. This is M. Okay, this one M2 25.7, 35.7, and then MO1 plus 0.5 M2. Our MO1 is here, 30.6. Okay, 30.16 plus okay 0.5 M2. M2 is equal to okay, this one M2 is equal to 35.7 divided by 5, 2, okay, to 35.7 divided by 2, and N minimum. N minimum is 12.5, okay, between 12.5. So this is the situation, okay, all four options, okay. So we can get here is we must choose the maximum between these four, 40.16, and then this one you get this value 41.76, 41.76, and then 43.01, 43.01, and then 12.5. So the maximum is this one, 43.01 as our design moment. So the similar process, okay, how as a previous example, but in this case we use okay, chart 0.25, and then for this, okay, I'm not sure what is why the value is 0.67, but this one is equal to this one, okay, okay, nearly close to the W, okay, as this one is equal to yes, if you still remember, the value of W is equal to this one 0.52. Okay, this is can you see AS over AS times FYK over BHFCK is equal to this one. Okay, AS the AC means BH. Okay, so equal to AS, not equal, actually AS FYD is equal to 0.87 FYK. Okay, divide by AC FY FCD. Okay, FCD. Okay, so you must redo the calculations, and then you get the KR 0.67. So once the KR is 0.67, so this value is changed. Okay, the KR is 0.67 here, this one. So the value here is the new value. This is the KR here is 0.67. Okay, the value of 1 over R is changed. So the value of the M2 is changed, and then you can get the new MED is equal to 40.16. So you must take a look back, okay, how to determine the value of KR is equal to 0.67. Okay, if not, you can just straightforward based on this value, because we use this value, we want to reduce the value of ASFIK over BH. Okay, we make it 0.45, so we can reduce the area of shear reinforcement. So the process is similar to the previous example. So you can, let's just assume that, this is the H, B, this is the B is equal to 250 actually, and H is 200, then be careful, be careful, you see here, H to the power of 2, so it's 200 square, so be careful of the value of H, so you must use this rule of thumb is very, very important, so it's similar to the previous, you check the S min and S maximum, so make sure that the S provided is within the range of minimum and maximum, and then you can select this one. This is similar because we have H12 here, so this is the lesser of H12, the lesser dimension of the beam, and the maximum is 500. So outside the critical region here, you can use H6 200, and at the critical region here at 250 mm above the beam, and also at the lapping, this one we call it as lapping, where this is the starter bar, and then another for the new story, we install another bar, and then we type together. This is we name it as lapping. At the lapping zone, and at the 250 mm above and below the beam 250 here, so the spacing shall be closer, which is equal to 0.6 times 200, so it's 120. So this is impractical, make it 100. Class, any questions for this one? It's I will refer back on how to, this is very, very critical. But I think in the exam you don't have to recheck the KR. KR will be given. KR shall be given. So you just straightforward from this one. You just determine from AS FYK over BH FCK. You can directly determine the AS required, and then you can propose the AS provided. That's all. Thank you very much for your attention. See you in next video, which is example 5.5, the design of non-slender columns with the biaxial bending. So thank you very much.